We have shown that the concept of a vertex of a polyhedron, which is a geometric concept, is equivalent to the concept of a feasible basic solution, which is an algebraic concept. However, there is not necessarily a bijection between the two sets. We show in this video that a vertex can actually correspond to several feasible basic solutions. This phenomenon is called degeneracy. Let's illustrate this on an example. So consider a polyhedron in R2 so that we will be able to plot it to make an illustration. Let's say the polyhedron is defined by the following constraints: x1 plus x2 less or equal to 1, and x1 is between 0 and 1, and x2 is also between 0 and 1. Okay, somehow if x1 is here and x2 is here, this is basically represented by this area here. Okay, so this is a triangle. In order to be able to calculate a feasible basic solution, we need to write this polyhedron in standard form. To do this, we will introduce a slack variable x3 for this constraint, another one x4 for this constraint, and x5 for this constraint. So what we obtain is x1 plus x2 plus x3 equals 1, x1 plus x4 equals 1, and x2 plus x5 equals 1. And all variable x1, x2, x3, x4, x5 must be non-negative. So this is the representation in standard form of the triangle that we have plotted here. So now we need to write the matrix A so that we can start calculating a feasible basic solution. So the matrix A, so it will have 3 rows, which are the 3 constraints, and 5 columns, which are the 5 variables. So the first row corresponds to the first constraint. For x1, the coefficient is 1. For x2, the coefficient is 1. For x3, the coefficient is 1. x4, it's 0. x5, it's 0. The second constraint, x1, 1. x2, 0. x3, 0. x4, 1. And x5, 0. And finally, the last constraint, we have 0, 1, 0, 0, 1. And the vector b is equal to 1, 1, 1. So now that we have this representation, we can select basic variables and calculate the basic solution. In the first example, let's select x1, x3, and x5 to be in the basis. Okay, so we extract these 3 columns from the matrix in order to form the matrix B. So that's what I will do in the next slide. Okay, so we have the matrix A, the vector B that we have just calculated, and we have these 3 columns that we have identified in order to calculate the feasible basic solution. So the matrix B is equal to 1, 1, 0, 1, 0, 0, 0, 0, 1. And then we can calculate xb, which is equal to b minus 1b, so the inverse of b times the vector b, and you can verify that it's equal to 1, 0, 1. So what is the value of x? So we have x1, x2, x3, x4, x5. Now we have calculated the 3 basic variables, which is x1, so x1 is equal to 1. Then we have x3, and then we have x5. And for x2 and x4, because they are out of the basis, they must be equal to 0. So the vector x, which is the basic solution that corresponds to this basis, is the vector 1, 0, 0, 0, 1. And it's non-negative, so it's feasible. So we have a feasible basic solution. So that corresponds to a vertex. Let's now calculate another basic solution. So let's select a different set of columns. So we now select x1, x4, and x5 to be in the basis. So it means that the matrix B is equal to 1, 1, 0, 0, 1, 0, 0, 0, 1. And therefore, xb, which is equal to b minus 1b, we can show that it's equal to 1, 0, 1. So what is the x vector that corresponds to this? Well, we have x1, x2, x3, x4, x5. Now we have calculated the value of the basic variables, which are x1, x4, and x5. So it means that x1 equals 1, x4 equals 0, and x5 equals 1. Now what about x2 and x3? Because they are non-basic variables, they must be equal to 0. So the vector x that we obtain is 1, 0, 0, 0, 1, which is non-negative, so it's a feasible basic solution. But this is the exact same vector that we have obtained previously. So we have considered two different sets of indices, that is, two different bases, and the associated solution, which is a feasible basic solution, is exactly the same. So it means that we have obtained the same vertex of the polyhedron. Let's interpret this on the picture. So here we have the two axes corresponding to x1 and x2. And if you remember, when we activate a constraint in standard form, is the same as putting one of the variables to 0. So this constraint will be active when x1 is equal to 0. This constraint will be active when x2 is equal to 0. This is the constraint x1 plus x2 less or equal to 1. It is associated with the slack variable x3, and it will be active when the slack variable will be equal to 0. Then we have the constraint that says that x1 is less or equal to 1. It is associated with the slack variable x4, and again this constraint will be active when x4 equals to 0. And finally, we have the constraint x2 less or equal to 1, which is associated with the slack variable x5, and the constraint will be active when x5 is equal to 0. And the intersection of all these constraints is this triangle. This is the polyhedron that you are looking at. Now the solution that we have calculated using the two bases is 1, 0, 0, 0, 1. If we want to represent it on the picture, well, we have x1 equals 1 and x2 equals 0. This is this solution. And actually we can see that x2 equals 0, so the constraint is active. But we can see also that x3 is equal to 0, so this constraint here is active. And x4 is equal to 0. This constraint is active. So I have three active constraints at that vertex. Now if you remember the geometrical interpretation of the basic solutions, the idea is to identify a vertex by deciding which constraints will be active. So in the context of basis 1, the non-basic variables are x2 and x4. So basically what we have done by choosing basis 1 is to set the constraints x2 equals 0 and x4 equals 0. And actually this was sufficient to identify the vertex. The fact that x3 equals 0 in this case is just a coincidence. It's not because we have decided to activate these constraints. It's because the constraints are such that it happens to be 0. And now if you look at the second basis, in the second basis, the two variables which are out of the basis are x2 and x3. So it means that in this case, I have decided to activate x2 again, but now I have decided to activate x3 equals 0. And it is again sufficient to choose two constraints to activate in order to identify the vertex. For the second basis, the fact that x4 is equal to 0 is just a coincidence. It's not because we have decided to do so. We could have reached the same results by choosing x3 and x4 to be out of the basis. So we could have chosen a third basis, which would be 1, 2, 5, and we would have obtained again the exact same vertex. Geometrically speaking, it would have been obtained by activating this constraint, and again the intersection is this same vertex. So we see here that the same vertex can be associated with several bases. And in this case, what happens is that one of the basic variables is equal to 0. Not because we have decided to set it to 0, like we do for the non-basic variables, but because the equation to calculate the basic variables happens to provide 0 as a solution. We will see later that it can be a problem because in this case we may generate directions which are not feasible. So we'll have to worry about this later on. So let's see the formal definition of degeneracy. So we have a polyhedron which is defined by a matrix A and a vector B and is written in standard form. We will say that a basic solution X is degenerate if there are more than n constraints that are active at X. So if you take a basic solution, how many constraints are active? You have the equality constraint, so you have m constraints which are active, and you have also activated the non-basic variables, that they are all set to 0. We have n minus m of them. So the total number of constraints that are active by design is equal to n. So what the definition says is that if the number of active constraints is equal to n, then we have a non-degenerate solution. If we have more constraints that are active, meaning that we have some k such that xbk is equal to 0, then the solution is degenerate. So this is the second part of the definition. We can also say that there are more than n minus components of x that are 0. In other words, we have some basic components of x that are 0. So there is not necessarily a one-to-one relationship between the feasible basic solution and the vertices. We have seen that if one of the basic variable is equal to 0, you can obtain the exact same vertex using several bases. This actually may be an issue when we will use this representation in the algorithm, and this will be analyzed later on.